Welcome, everyone. In this lecture, we are going to study one of the most fundamental topics in circuit theory, Kirchhoff's laws. These two laws are the very backbone of circuit analysis. Whether you are dealing with a simple resistive circuit or a complex network, Kirchhoff's laws will always be your starting point. So let's get into it.
Before we talk about Kirchhoff's laws, we need to be very clear about the terminology used in circuit theory. Let's define the key terms. A network is simply an interconnection of elements or devices. Now, if that network provides one or more closed paths for current to flow, we call it a circuit. A branch is a single element, like a voltage source or a resistor. Each individual element in a circuit is one branch. A node is the point where two or more branches are connected. You will usually see it marked as a dot in a circuit diagram. Here is an important note. If a short circuit, that is, a wire of zero resistance, connects two nodes, then those two nodes are treated as a single node. Finally, a loop is any closed path in a circuit. You start at a node, travel through a set of other nodes, and come back to the starting node without passing through any node more than once. Now there is one more concept, an independent loop. A loop is said to be independent if it contains at least one branch that does not belong to any other independent loop.
Let's look at this circuit on the left. Your task is to identify the number of nodes, branches, and loops. Look carefully at the circuit. How many nodes are there? Count them. There are 3 nodes in this circuit: A, B, and C. You can verify this by looking at the junction points highlighted. Notice the 3 distinct connection points. One thing to observe here is that 2 nodes that are connected by just a wire, a short circuit, collapse into one single node. Keep this in mind when you count nodes in any circuit. Count the branches. There are 5 branches. Count the independent loops. There are 3. The independent loops are: loop 1 is 5 ohms resistor, 2 ohms resistor, and 10 volt source. Loop 2 is 5 ohms resistor, 3 ohms resistor, and 10 volt source. And loop 3 is 5 ohms resistor, 2 ampere current source, and 10 volt source. Now let's apply the fundamental theorem of network topology to verify our analysis. The theorem states B equals N plus L minus 1, where B is the number of branches, N is the number of nodes, and L is the number of independent loops. In this circuit, branches, B equals 5. Nodes, N equals 3. And applying the formula, 5 equals 3 plus 3 minus 1. This checks out, confirming that there are 3 independent loops. Now look at this second practice problem. Let's analyze the circuit on the left. Branches equals 4. Each element is a separate branch. We have 10 volts voltage source, 5 ohm resistor, 6 ohm resistor, and 2 amp current source. Nodes equals 3. The 3 nodes are at the top left, top right, and the bottom rail, which is the common ground. Let's verify with the network topology formula. B equals N plus L minus 1, which gives 4 equals 3 plus 2 minus 1. This is satisfied, confirming 2 independent loops. In this problem, we have a slightly larger circuit. Let's count again. Branches equals 5. Each element is one branch. They are 1 ohm resistor, 2 ohm resistor, 5 ohm resistor, 10 volts voltage source, and 4 ohm resistor. Nodes equals 3. The 3 nodes are the top left junction, the top right junction, and the bottom rail, which is the ground. Applying the formula B equals n plus L minus 1 gives 5 equals 3 plus 3 minus 1. So we have 3 independent loops in this circuit. Now we come to the main topic. Kirchhoff's laws were introduced in the year 1847 by the German physicist Gustav Robert Kirchhoff, who lived from 1824 to 1887. Together with Ohm's law, these two laws give us a complete and powerful toolkit for analyzing almost any electrical circuit. There are two laws. Kirchhoff's current law, or KCL. This is based on the conservation of charge. It states that the algebraic sum of all currents entering and leaving a node must equal 0. In other words, KCL governs the current behavior at every node in a circuit. Kirchhoff's voltage law, or KVL. This is based on the conservation of energy. It states that the algebraic sum of all voltages around any closed loop must equal 0. KVL governs the voltage behavior in every loop of a circuit. Remember this clearly. KCL is for nodes, KVL is for loops. This distinction is very important. Let us now go deeper into KCL. The mathematical statement is the algebraic sum of all currents at a node equals 0. We write this as the summation of I sub n equals 0, where the summation is from n equals 1 to n. N is the total number of branches connected at that node, and I sub n is the nth current either entering or leaving the node. Now, the sign convention is important. Currents entering a node are taken as positive, and currents leaving a node are taken as negative. Or you can use the opposite convention, entering negative, leaving positive. Both are equally valid. The result will be the same as long as you are consistent throughout your analysis. The physical basis of KCL is the conservation of charge. Charge cannot be created or destroyed at any node in a circuit. Whatever charge flows in must flow out. Let's see how to actually apply KCL with an example. Look at the circuit on the left. We have a node with 5 branches. Currents I1, I3, and I4 are entering the node, while currents I2 and I5 are leaving the node. Step 1. Apply KCL directly, using entering as positive, leaving as negative. I1 plus minus of I2 plus I3 plus I4 plus minus of I5 equals 0. Step 2. Rearrange. Move leaving currents to the right side. I1 plus I3 plus I4 equals I2 plus I5. This gives us the key insight. The sum of currents entering a node always equals the sum of currents leaving it. This is the most intuitive way to remember KCL. Think of water flowing through a pipe junction. Whatever flows in must flow out. And remember, the sign convention can be reversed. You can choose entering as negative and leaving as positive. The final equation will give the same result either way. Now let us see how KCL is used to combine current sources. We have a circuit with 3 current sources connected at node A. Applying KCL at node A, using entering equals leaving, we have I sub t plus I sub 2 equals I sub 1 plus I sub 3. Rearranging, we get I sub t equals I sub 1 minus I sub 2 plus I sub 3. Here, I sub 1 and I sub 3 are entering node A, so they are added. I sub 2 is leaving node A, so it is subtracted. I sub t is the equivalent combined current source that replaces all 3 parallel sources. This is a very practical result. When you have multiple current sources in parallel, you can replace them with a single equivalent source whose value is the algebraic sum of all individual sources, taking polarity into account. Important note, series constraint. Two different current sources placed in series is a problematic configuration. KCL demands that the same current flows through every element in a series path. So if two different current sources of different values are placed in series, KCL will be violated. This is not allowed in circuit theory.
Now, let us study KVL in detail. The mathematical statement is: the algebraic sum of all voltages around a closed loop equals 0. We write this as sum of V sub m equals 0, where the summation is from m equals 1 to m. M is the total number of voltages in the loop, and V sub m is the mth voltage encountered as you traverse the loop. The sign convention for KVL is: a voltage rise is treated as positive. A voltage drop is treated as negative. Again, the reverse convention, rise negative, drop positive, also works as long as you are consistent. The physical basis of KVL is the conservation of energy. Energy supplied by the sources must equal the energy absorbed by the resistors and other passive elements around every closed loop.
Let's apply KVL to a circuit. On the left side, you can see a circuit, and we will traverse it clockwise, starting from the voltage source. The sign rule for KVL we use here is: if you encounter the positive terminal first while traversing, the voltage is added as plus V sub m. And if you encounter the negative terminal first, the voltage is added as minus V sub m. Step 1. Apply KVL clockwise, encountering the negative terminal of V1 first. Minus V1 plus V2 plus V3 minus V4 plus V5 equals 0. Step 2. Rearranging V2 plus V3 plus V5 equals V1 plus V4. This gives the key insight. Sum of voltage rises equals sum of voltage drops around any closed loop. For example, as we traverse the circuit, branch 3 is entered from the positive terminal, so we write plus V3. Branch 4 is entered from the negative terminal, so we write minus V4. Important point: you can choose to traverse the loop clockwise or counterclockwise, and you can start from any branch. KVL holds regardless of the direction of traversal or starting point. Just be consistent with your sign convention throughout. Finally, let's see how KVL is used to combine voltage sources. We have a circuit with three voltage sources V1, V2, and V3 in series. Applying KVL around the loop, encountering the negative terminal of V sub AB first, minus V sub AB plus V1 plus V2 minus V3 equals 0. Rearranging, V sub AB equals V1 plus V2 minus V3. Here, V1 and V2 are in the same polarity direction. They add up, aiding sources. V3 is in the opposing polarity direction. It subtracts, opposing source. And V sub AB is the single equivalent combined voltage source. This means when you have multiple voltage sources in series, you can replace them with one equivalent source. Sources of the same polarity add, and sources of opposite polarity subtract. Important note: parallel constraint. Two voltage sources of different values placed in parallel will violate KVL, because KVL demands that the voltage across two parallel elements must be equal. So two ideal voltage sources of different values cannot be placed directly in parallel. This is not physically realizable. To summarize the series combination rule, series sources combine algebraically. Aiding sources add, opposing sources subtract. Summary of this lecture. That brings us to the end of this lecture on Kirchhoff's laws. Let's quickly recap. 1. Nodes, branches, and loops are the building blocks for describing any circuit. The network topology relation B equals n plus L minus 1 connects them. 2. KCL, based on conservation of charge, states that the algebraic sum of all currents at a node equals 0. 3. KVL, based on conservation of energy, states that the algebraic sum of all voltages around a closed loop equals 0. 4. KCL helps us combine parallel current sources. KVL helps us combine series voltage sources. 5. Two current sources of different values cannot be in series. Two voltage sources of different values cannot be in parallel. These two laws, together with Ohm's law, form the foundation of all circuit analysis.